Okay, so good morning, Alpha. So today we are going to talk several types of flow measurements, including Pitot tube, and then Venturi meter, and then orifice meter, and then Roteflow, and some other flow measurement devices. Okay, so for the first subchapter here is the Pitot tube. Yeah, so we will start with the next slide. Yeah, so Pitot tube consists of a tube pointing to the fluid flow. So there are two types of Pitot tube. First is simple tube, and the second is tube with static pressure holes. Yeah, so you please open your Juan list while we are discussing about these courses. Yeah. Okay. So I will let me go to the Juan list. So as you can see, there are two types of Pitot tube here. Yeah. So in figure T321A, and this is the common Pitot tube, the simple one. The simple tube here. And then for point B is the tube with static pressure holes. Yeah. Okay, so when we go here, yeah, we have to, when we go to the point A, yeah, there are two openings. Yeah, one for the static tube. Yeah, so the flow inside the pipe will fill in the static tube, yeah, while the impact tube will receive the flow from the middle of the pipe, yeah, and it will push harder usually as compared to the static tube because it will give it will only receive a slow motion flow, yeah, because of the the flow near the wall usually do not have like fast velocity, so it will only give a small pressure, while the one in the middle usually have a larger velocity, so it will give more impact, yeah, and give more push, yeah, to the manometer. Okay, now, okay, while for the tube with static pressure, it will only have one impact tube, yeah, so it will push the liquid, yeah, inside the manometer, and it will fill, yeah, it will fill with the static. This is also have two actually, the tube, yeah, here as well, yeah, there is an opening on the outer part, yeah, of the impact tube, yeah. Okay, but it's only to release out the liquid from the static tube, yeah. Okay, so but as you can see here, it's only have one, there is no opening there, yeah. The opening is only the outer part, which is to release the remaining liquid which is retained in the static tube. Okay, yeah. Okay, I will go back again to the PowerPoint. Yeah, nah. So Pitot tube, yeah, is used to measure the velocity at a given point in the flow stream. Yeah, so if it's inside the pipe and you put the Pitot tube in the middle of the pipe, then you will only measure the velocity at the middle of the pipe. Yeah, so they will not measure the average velocity in the pipe. They will only measure the velocity at a given point in the flow stream. Yeah? Okay, so if you put it near the wall, then they will only check the flow rate near the wall. If you put it a little bit higher on near the middle part of the tube, of the pipe, then pitot tube will only measure at those exact points. Yeah, they will not check on your total average velocity. Okay. Nah, so how pitot tube works? Yeah, so the fluid flow, yeah, in the pitot tube. Yeah, so if you have a pipe, let's see, this is the upper wall of the pipe, the bottom wall of the pipe, and there is a velocity here, yeah, of the fluid, and you put the pitot tube, the opening is in the middle, exactly in the middle, right here. Now, so the fluid flow in the fluid will flow into the pitot tube via the opening of the second point here, yeah, and build pressure. So it will build pressure, yeah, to push down the flow. Sorry, to push down the liquid in the manometer. Yeah, it will remain stationary at this point. Yeah, now point 2, yeah, in this figure is called as a stagnation point, and we call the pressure as a stagnation pressure. Yeah. And then the velocity, yeah, of the fluid, yeah. So there is a velocity as well, yeah, close to the perpendicular opening of the pitot tube, the static tube here. Yeah. Yeah, so this is stagnation point. Yeah, it will push down. Yeah, we call it as a stagnation pressure. While we have also a velocity of fluid, yeah, close to the perpendicular opening of the pitot tube. Yeah, so we call this as a static tube. Yeah. Usually it is 0. Why? Because it's near the wall of the pipe. So if we call this as a stagnation pressure, we call this as a static pressure. Yeah. Now, the difference between the static pressure and also the stagnation pressure is associated with the deceleration of the fluid. Yeah. And also to the flow rate. Yeah. So the difference between the pressure here, sorry. Yeah, between the pressure here and the pressure here, yeah, it can be directly related to the flow rate. Yeah. Nah, okay. So when we want to calculate, yeah, either the velocity of the point 1 and point 2, the delta pressure, because the delta pressure really determines the flow rate. Yeah. So the manometer here, yeah, usually will be used to check on the delta P, right? And the delta P is directly correlated with the flow rate passing through the pipe. Yeah. Okay, now if the fluid is incompressible or a liquid, yeah, so the Bernoulli can be applied, yeah, in point 1 and point 2. Yeah. And since point 1 and point 2 is in the horizontal line, yeah, so there is no Z, yeah, Z1 equal to Z2, yeah, so I can scratch this off from the equations, yeah, so what we have left is only this velocity 1 and velocity 2 as well as the delta P, yeah, over density, yeah. Okay, so after some rearrangement of the Bernoulli equations, then I can get this equation. Yeah. Okay. Nah, at point 2, yeah, we must know that the velocity at this point, exactly at the opening of the pitot tube, yeah, that's why it is called stagnation point, because it doesn't have any velocity. In point 1, they have velocity, yeah, because it's just before it reaches the opening of the impact tube. Yeah, so that's why it's not 0. However, however, at point 2, yeah, that's why we call it as a stagnation point, because there is no flow, yeah, in the exact place of the opening, yeah, of the impact tube. So that's why the point 2 has 0 velocity, so V2 equals to 0. Yeah, so V2 equals to 0. Yeah, so what we have left is only V2 squared over 2 equals to delta P over density. Yeah. Nah, okay, so after I move the 2 to the other side and then square root, because previously it's V2 square, right? Okay, so I get these equations. Nah, however, yeah, since usually the calculation, yeah, will have, you know, the flow inside the pitot tube usually will have a friction, yeah, friction loss, yeah. So of course there will be a deviation in the calculation. Yeah, since we have the deviation in the calculations, yeah, we can use CP, yeah, as the coefficients to minimize the deviation. Yeah, so this CP, yeah, actually is a coefficient that will be given in the problem. Yeah, the value ranges from 0.8 up until 1. Yeah, okay, it's 0.8 up until 1, and it depends on the problem. Yeah, and usually it will be known in the question. Yeah. Okay, so CP itself is the coefficient, yeah, to make up for the friction loss, skin loss, yeah, and etc. And in order to minimize the deviations in the calculation. Yeah, nah, this equation can be also used not only for the liquid but also for gas. Yeah. However, we have to make sure that the pressure change here, yeah, is not higher than 10%. Okay. Yeah. So when you want to use these equations for gas can, but the delta P cannot be higher than 10% of the total pressure. Yeah, if it's higher, then we cannot use this one because this is only for incompressible fluid. Yeah. Nah, and then previously I told you that the delta P, yeah, directly correlates to the flow rate. Yeah. So to calculate the pressure drop, yeah, we can use this, yeah, delta H in the manometer times rho A. Rho A is the density of the fluid used in the manometer. Yeah, so if I have a manometer, yeah, this, yeah, rho A is this, yeah, this is rho A. While rho, yeah, rho is the fluid passing through the pipe. Yeah, okay, so this is rho. Yeah, rho A is the density of the fluid inside the manometer, while rho is the density of the flowing fluid in the pipe. Yeah, times gravity. Okay, delta H the manometer reading. Yeah, in meter. Yeah, so it's sometimes it's in centimeter, it's in millimeter, but you have to convert it to meter first. Yeah, use SI. Yeah, then you can get the pressure drop. Okay, now, as I previously mentioned, that pitot tube can be only used to measure the velocity at a certain point, but not the average velocity. Now, how to calculate the average velocity then? Yeah. Nah. So many uses these two methods. Yeah. First, after you find the velocity at the center of the pipe to gain Vmax, yeah, so we put the pitot tube at the center line because by then we can measure the velocity maximum. Yeah. Now, then after we use the velocity maximum, then we can try to find the Reynolds number using the velocity maximum. And then by using figure 2.102, we can find the velocity average. Yeah, so I will try to move to this John Goplis again. Let me go to page, let's say 93. Oh no, 90. Oh, this one. Yeah, this. Yeah. So after you find the Vmax, then you can try. Then you can find this, the NRE max. Yeah, here. Yeah, the NRE max. Yeah, after you find the NRE max. Yeah. Okay, this is NRE max. I will go up to the NRE max, or after it reaches. Yeah, after it meets the curve of the NRE max, then I will draw a straight line to the left to find the V average over Vmax. Now, if I know the Vmax already because of the pitot tube, then by using the ratio between V average to Vmax, then I can find the V average. Yeah, okay, like that. Yeah, that's the first method. And the second method is to use the integration equation. Yeah, but for me, I prefer the first one because it is easier. Yeah, okay. If you have any questions, please write down in the comment below. Yeah, or you can directly chat me. And we go to the example 3.21. Okay. Okay, nah. Where is it? Oh, yes. Nah, yeah. So we have a pitot tube, yeah, similar to the simple tube, yeah. It's used to measure the airflow, yeah, the airflow in a circular duct with the diameter of 600 millimeter. Yeah, the flowing air temperature is 65.6 degrees Celsius, and the tube is placed at the center of the duct. So what we have later, the velocity is the velocity max. Yeah, and the reading delta H on the manometer is 10.7 millimeter of water. Nah, a static pressure measurement, so the one in, here, let me show you. Yeah. Nah, here, yeah. So that static pressure measurement obtained at the pitot tube position is 205 millimeter above the atmospheric. So it has a pressure higher than the atmospheric because they said it's 205 mm of water above atmospheric. Yeah. Now the pitot tube coefficient CP is 0.98. I said to you, it should be known from the problem. And then we are asked to calculate the velocity at the center, which is Vmax, and the average velocity. And then we are also asked to calculate the volumetric flow rate of the flowing air in the duct. Okay, so for part A first, yeah, we know the air temperature is 65.6. Yeah, so based from the appendix A3, I can find the density and viscosity of the air. Yeah, now, but this is both of the mu and rho is at 180 m. Yeah, while the static pressure is actually not 180 m, but it's higher because it has 205 millimeter of water above the atmosphere. Now, therefore, to calculate the absolute static pressure, yeah, I have to find the delta P, right? To get the actual pressure, yeah, in the system, yeah, not because of the flowing air, but in the system itself, yeah. Now, okay, so I will use the equations 2.214, yeah, 2.214, or I can just say that I will use the equations of 323, yeah, that rho times G times delta H, rho A minus rho times delta G times delta H times G. Yeah, okay. So the delta H is 20205 because I need to change from millimeter to meter. And then this is the G, gravity, right? And then here, yeah, the water density I assume as 1000, yeah, because we don't know the temperature of the water, yeah. And then for air, yeah, for the air, it's 1.043, yeah, this, yeah, at 180 m, at 180, okay. For me to find the delta P, and then after I find the delta P, then I know the actual P, yeah. So I use 1.043 because 1.043 is at 180 m. Right. Okay, so I put all, then I can find all. The delta P is 2008 Pascal. So I will add the 180 m here with this 2008 Pascal. Yeah, so I found that, oh, it's 1.0333 times 10 to the power of 5 Pascal. So by using the new static pressure, by obtaining the new absolute static pressure, then I need to find the density of the air, yeah, because air is gas, yeah, air is gas. So changing in the pressure will change the density, while for liquid usually it will not really significantly different, yeah. Okay, so I use the, the correlation, yeah. I use the comparison, yeah. So the new pressure over the old pressure times the old pressure equals to the new density, yeah. So old new pressure over the new pressure over the old pressure times old density, we get then we can get the new density, yeah. So after I find the new density, yeah, I put to the same equations again, which is delta H times rho A, or the density of the liquid inside manometer, minus rho of the flowing air times G, we can get the delta P, yeah, for the flow, yeah. Okay, so it's 10.7 divided by 1000 because I need to convert millimeter to meter. And then this is the liquid density, yeah, the water density inside the manometer minus the new density of the flowing air, yeah. K times G, then we can get it's 104.8 Pascal. Yeah, nah. So after I knew this, then I will put it in this equation. Yeah. Okay, so I know delta P is 104.8. I know the density of the flowing air, the new one, times 0.98. Yeah, it is known from the problem. Yeah, then I can find that the velocity is 13.76. Now, then I will use this first technique. As I said to you, it's easier. I need to find the NRE max. Yeah, so this is the max velocity. Okay, the diameter I know it's 600 millimeter. Yeah, I need to change it to meter. And then rho and mu, I know it from the appendix. Yeah, and this from the correlations previously, right? So I found it to be this, the NRE. Yeah, and by using the figure of 2.102, yeah, I can find that the V average over V max, yeah, in this Reynolds number is 0.85. Since I know V max and I know the ratio between V average to V max, then I can find the V average, which is at 11.7. Yeah. Now, and for point B, yeah, calculate the volumetric flow rate of the flowing air in the duct. Okay, so by using this 11.7 as the average, yeah, I can just directly multiply it with the, this is the volumetric flow rate, yeah, the one that is asked. So I need just to find the cross-sectional area of the duct, of the circular duct, yeah. So the cross-sectional area is pi over 4 times diameter square, right? So it becomes this, and multiply it with this, I can find this, yeah. So that's for pitot tube, okay. Okay, if you have any questions, please drop the message in the comment section below, or you can just directly chat me. So now we go to the second topic, which is about the Venturi matter. Okay, so actually the Venturi matter and olivine matter, which is I will also describe right after this, are quite similar to each other. However, the shape of the devices is a little bit different, but the concept is quite similar. Yeah. Nah, so for Venturi matter, nah, the shape is like this. Yeah. Yeah, the shape is like this. Yeah, it's usually this system. Yeah, this system is usually inserted into the pipeline. So we have pipeline on the upstream, yeah, on the left. We have also another pipeline on the right, and in the middle we will put this Venturi matter system. Yeah, so this usually insert into a pipeline and connected into a manometer. Yeah. Now, as you can see here in P1, yeah, in point 1, yeah, it has a velocity 1, and then it's not surface area, cross-sectional area 1, yeah, and it also have their own pressure 1, yeah, while in the neck, yeah, or point 2, yeah, it has their own cross-sectional area, which is, as you can see from the diagram, is smaller than point 2, but of course the velocity at this point will be higher as compared to the velocity 1, and it also has a pressure 2, yeah, okay, which is higher than pressure 1. Yeah. Nah, okay, so how it works, yeah? During the movement from the left to the right, yeah, the diameter 1, yeah, will narrow down to diameter 2. Yeah, so that's why, as I said to you, the area 1 will narrow down to area 2. Yeah. Okay, nah, but there is also expansion. Yeah, so after it is compressed, yeah, in this neck, yeah, it will be expanded again from area 2, yeah, to this part, yeah, to this right part of the pipe, yeah, which has a similar diameter of 0.1. Yeah, so after in 0.1, it has a bigger area and then it's compressed to area 2, it will be expanded into area 1 again. Yeah. Okay. Now, because of the expansion, yeah, and also contraction, yeah, there will be a friction loss, yeah, pasti, yeah. So because of the compression and then expansion, there will be friction loss, yeah. However, as you can see from this shape, yeah, the expansion and the contraction is gradual. Yeah, it's not just directly expand or directly has a sudden contraction. No, yeah, it is gradual. Yeah, there is a slope here. Yeah, a slope again here. Yeah, so even though they have a friction loss, but only a little friction loss will incur, that will occur. Okay. Okay. Now, because of this expansion and contraction, yeah, in the manometer, there will be a change in the pressure, yeah, between 0.1 and 0.2. Yeah, therefore, later, yeah, this pressure again will directly show or directly related to the flow rate. Yeah. Okay. Nah. Okay. To derive the equations for the Venturi method, yeah, several assumptions are taken into account. So first is that the friction is neglected because of the gradual expansion and gradual contraction, yeah, in this system. Yeah, and then pipe again is assumed to be horizontal. Yeah, it is horizontal. Yeah, only the size are different. And then the third is the flow is assumed to be turbulent. So during all of this part of the Venturi method, the flow is assumed to be turbulent. So making the mechanical energy balance for incompressible fluid to be a Bernoulli equation again. Yeah. So since there is no sloping, yeah, since pipe is assumed to be horizontal, there is no Z1 and Z2 in the equation. Yeah, so only velocity and pressure. Yeah. Okay. Okay, I will open all first. Oh, sorry. Nah. So after we have this equation, yeah, after we have these equations, yeah. Now we have also one continuity equations for constant pressure. Yeah. So if I have a constant pressure, yeah, between P1 and P2, yeah, actually we will know that the mass flow rate, yeah, the mass flow rate between this side and this side will be the same. Yeah, because there is no additional mass added and there is no removal of mass from the system, right? So of course, the mass here and the mass here will be the same. Yeah. And since the mass are the same, also there is no change in the material, right? If it's water, will it become oil here? No. Yeah, it will also be a water. Yeah. So the density will be the same. Yeah. Since the density will be the same and mass are the same, so the volumetric flow rate will be the same. Yeah. Now, the volumetric flow rate in point 1 and point 2 will be the same, but since the area of the pipe are not the same, then the velocity will not be the same. Yeah, nah, so that's why for the continuity equations, we can say that Q1 equals to Q2. Yeah. Q1 equals to Q2. Yeah. The volumetric at point 1 equals to the volumetric at point 2. Since Q, yeah, equals, yeah, in general, Q equals to V times A, yeah, velocity times area, then I can say that V1 times A1 equals to V2 times A2, right? Okay, so I will expand this again. V1 times A1. A1 is the area of the pipe at point 1. So P times D1 square over 4 equals to V2 times pi diameter 2 square divided by 4. Yeah. Okay. Now, by using the first equations in the previous slide, Bernoulli equations, and these equations, equation 2, yeah. Then after I combine both, I can find this equation. Yeah. Okay, so after substitution and also mathematical arrangement, then I can get this. Okay. Nah. However, since I previously said, yeah, the Venturi method has also a friction loss. Yeah. So that's why it cannot be just directly 1. We have to change it to CV, or the constant for the Venturi. Yeah. If in pitot we know CP. CP is coefficient for pitot tube P, right? Pitot is P. Yeah. Well, this I use CV. CV is coefficients for the Venturi method. Yeah. So I changed once to CV. Yeah, no. Okay. It is used, yeah, CV is used, yeah, to account for the small friction loss, yeah, because it's not, because we cannot say that there is no loss at all. Yeah, there is a loss. Yeah. That's why we change it. We change that 1 into CV. Now, the value of CV, yeah, with the respect of the pipe and also Reynolds number, yeah, is this, yeah. So for Reynolds number higher than 10,000, yeah, at 0.1, yeah. So the CV for a diameter of 0.2 meter is 0.98, yeah. However, if the pipe has a diameter of higher than 0.2 meter, the CP when the Reynolds number is more than 10,000, it's 0.9. So both of this, yeah, must have the NRE of higher than 10,000. Yeah. So if the diameter of pipe at 0.1 is less than 0.2 and has the Reynolds number of higher than 10,000, the CV is 0.98. However, when the NRE is higher than 10,000 and the pipe diameter at 0.1 is higher also than 0.2 meter. Yeah, the CV is not 0.98 anymore, but it's 0.99. Okay, then the volumetric flow rate. Yeah, the volumetric flow rate, yeah, can be found using equations 3.28, where V2, yeah, since volumetric flow rate is Q, right? Q is V times area, right? So that V2 times area 2, yeah, I can find the volumetric flow rate at point 2. Yeah. So I will go to this Chuanko, please. Yeah. Okay, yeah. Don't forget, yeah. In Venturi meter, yeah. If we use the English unit, don't forget with GC here. Okay, yeah. And CV, yeah. The Reynolds number must be higher than 10,000. CV is 0.98 for pipe diameters below 0.2 meter and 0.99 for higher than 0.2 meter. Okay, now if I want to find the flow rate, I will use this equation. Yeah, so just multiply the V2, yeah, with the cross-sectional area. Just that. That's flow rate. Yeah. Nah. Okay. Nah. While that's for incompressible fluid, right? Now, while for the compressible fluid, yeah, there is a correlation. Correlation. A correction factor. We call it as Y. Yeah. So it's to account the frictional loss. Yeah. And to convert the system to adiabatic. Yeah. Because we have to assume that the process is adiabatic so that it can be calculated easily. Yeah. Now, to convert the system to adiabatic as well as to account the frictional loss, yeah, we have to use this correction factor or Y. Yeah. And as I previously said to you in chapter 2 and also in chapter 3.1, yeah, if the flowing fluid is not incompressible fluid, but instead it's the compressible fluid, then the one that is constant is not velocity anymore. Yeah, the one that is constant is not velocity anymore, but the mass flux, ya, or the mass. Ya, so jadi kalau misal liquid kita biasanya pakai velocity nih. Ya, tapi kalau kita sudah pakai gas, ya, kalau sudah pakai gas, velocity itu sangat dipengaruhi oleh pressure soalnya. Ya, nah yang nggak dipengaruhi apa sama pressure itu adalah mass flux atau mass. Ya, nah, therefore, yeah, we do not use velocity anymore because velocity will be significantly affected by the pressure. Instead, we use mass here. Yeah. So previously for velocity, it's only this, right? With this in the denominator, isn't it? Yeah. Now, however, since it's mass, yeah, velocity times A, yeah, or cross-sectional area, we got the volumetric flow rate. Yeah, if we multiply it again with the density, the volumetric flow rate becomes mass. Okay, yeah, so this V, yeah, I multiply it with A, right? It becomes the volumetric flow rate, yeah. And I multiply it with density, it becomes mass. Miss, but the density should not be inside the Square root, yes, correct. Yeah, but I can change the one outside the square root becomes density square if I put it inside the roots, isn't it like this? Right? And since previously it has one density in the denominator, then I can erase this. So it becomes density inside the root, but in the nominator, not in the denominator, right? And I multiply it with y because it's the correction factor. Yeah. Nah, this correction factor or y, where do we get the value, Miss? Yeah. Will it be known in the problem? Sometimes yes, but sometimes you also have to find out yourself by using this figure 3.23 in GenGo, please. Yeah, so the 4 line here, it's for orifice. The 4 line in the below is for segmentary method. Yeah. So how to find, how to find the expansion factor? Yeah. So to find this, you have to know the two value, the two value. So first is the 2 over the 1, So if I know that d2 over d1 is 0.2, then I will use this line. If I know that the d1 over d2 value is 0.5, then it's this. But if I know the density, the diameter 2 per diameter 1 is 0.7, then I use this one. Nah, and then, this is pressure ratio So P2 over P1 teman-teman, not rho 1. Okay. Because the density will be the same in point 1 and point 2 because both have the same components. So P2 over P1, if it's 0.8, then this, if it's 0.9, it's this, 0.7, it's this, and so on. Okay. Then after, let's say it's 0.9 and 0.2, so it's this, right? It's this line. So draw a horizontal line to the left, and after it hits the y-axis, then you know the correction factor is 0.935. Let's say. Okay. Nah. Okay. Nah. Then so previously we know the V2, we know how to find the mass for a compressible fluid. Now we want to try to find the pressure drop, for the incompressible fluid. So following the Bernoulli principles, the energy at point 1 and the energy at point 2 is actually proportional. Because V1 over V1 square, right, over 2 plus P1 over rho equals to V2 square over 2 plus P2 over rho. So it's actually proportional, okay, which means, that the difference in pressure, between point 1 and point 2 is also proportional to the difference in height in the manometer. Okay. So it again translates to the equation of this, yeah, similar to what pitot tube says. Yeah, so its density, yeah, density of what? Yeah, the density of the manometer, let's say it's density A for manometer times gravity times delta H here. Yeah. While in terms of velocity, yeah, after some rearrangement of the Bernoulli equations, we can get this. Okay. Yeah. So the pressure drop is actually similar, yeah. The equations is similar. It's density times gravity constant 9.8, right? Times the height difference of the manometer. Yeah. Okay. Nah, the last slide for Venturi method. Yeah. Previously, I told you that there is a compression from point 1 to point 2, and then there is also an expansion from point 2 to point 3. Yeah. Nah, let's say we have, but previously for the calculations, we only really focus on 1 and 2, only the compression. Yeah? We did not see the expansion here. Yeah. Nah, so, but let's say in this case, we have a wide area where the point at the right side of point 2 is point 3. Yeah. Nah, the velocity, yeah, from point 1 to point 2, yeah, will be, which one will be higher? In point 2, yeah, velocity 2 will be higher than velocity 1. Yeah. Nah, however, after some expansion, yeah, from point 2 to point 3, yeah, the velocity at point 2, yeah, will be back to its original value in point 3. Yeah, because point 3 and point 1 has a similar diameter of the pipe. Yeah, so it will be back. Yeah. However, because of some frictional losses, yeah, there is a frictional losses, right? In the expansion, the contraction, there will be a frictional loss. Yeah. So V1 will not be exactly the same as V3. Yeah, so we cannot say that V1 is the same as V3. No. Yeah, it will not. Yeah, why? Because of the friction loss. Yeah. Nah, some pressure difference that may not be fully recovered to the original P1. Yeah. Therefore, the value of T3, yeah, the value of T3 is approximately 10% less than the original P1. Yeah. Okay. So if P1 is 100 kPa, P2 is 200 kPa. Yeah. Okay, then T3 will not be 100 kilopascal. Yeah, it will be 10% less than the difference of this. So the difference of this is minus 100 kilopascal. And multiply by 10%, it's minus 10 kilopascal. So in T3, it's not 100 kilopascal anymore, but only 90 kilopascal. So it's 10 kilopascal less than what the original P1 is. Yeah. Okay. Nah, this 10 kilopascal, yeah, is called as the permanent loss. Yeah, and it cannot be recovered. Yeah, because of the friction loss. Okay. Okay, so That's all for the Venturi method. Is there any question? Okay, so let me try to go back whether we have a, oh no, okay. We do not have any example. Okay, so I will go to the third, yeah, orifice meter, yeah. Okay, so orifice meter, as I said to you, it's similar to Venturi method, right? As you can see, yeah, it's similar to Venturi, yeah. However, orifice method has two machine drilled plate mounted, yeah, between the flank of the pipe. Okay, so this is the flank of the pipe. This one is flank, yeah. Okay, and then between the flank of the pipe, I have a two machine drilled. So it is drilled, yeah. It is drilled, yeah. The plate is drilled, okay, between the two flank, yeah, so that it has only a very small opening in the middle, yeah, with the diameter of DO, yeah. Yeah, so it's similar, yeah. If Venturi method is like this, right? It's the same, right? Pipe, yeah, pipe. Okay. But in Venturi, yeah, the expansion and also the compression, yeah, is done gradually, like this. Okay, gradually. Well, for this, no, yeah. Okay, so it's like this, thread, thread, yeah. So it's like a sudden expansion and a sudden contraction. Yeah, well, this is gradual contraction, gradual expansion. Yeah, for this, it's gradual. From this to this is gradual compression. From this to this is gradual. It's not gradual. Sudden contraction, sudden expansion. Yeah. Nah, again, similar to Venturi method, orifice is also connected to the manometer. Yeah. Okay. Nah, for the left pressure tab, ya. So, jadi kalau untuk manometernya orifice ini, yang sisi kiri, jadi sisi P1, ya, is usually installed one pipe diameter upstream. Yeah, so if the diameter is 1 meter, so from the plate mounted here to this opening for the manometer is also 1 meter. Yeah. Okay. Well, for the right pressure tab here, yeah, it's only 0.3 up until 0.8 pipe diameter downstream. So if it's 1 meter, so from the mounted plate to this manometer, yeah, on the right is only 0.3 meter up until 0.8 meter. Yeah. So it's shorter, yeah, compared to the right, to the left hand side. Okay. Nah, the measurement of flow for the incompressible fluid can be seen in 3.210 in Jankowitz. Yeah, so it's similar to 3.27, only the coefficients are different. I will show you. Where is it? Here, yeah. So it's exactly the same, teman-teman, ya. So it's exactly the same, but it's not CV, instead it's CO. Yeah, coefficients of the orifice. Okay. Yeah, while for the other are similar. Okay, phi O is phi at this O point. Yeah. Okay, DO is the diameter at this O. Yeah. Okay. Yeah. Nah. Okay. Oh, maybe I will go there. Yeah. Pressure drop. Yeah, this one. Yeah. So VO is the velocity at this point. CO is the coefficients of the orifice. Yeah. And then P1 minus P2. Yeah. So it's the pressure here and the pressure here. Okay. Nah. Okay. So the value of CO, yeah, is also usually known from the problem. Yeah. Nah, if the Reynolds number is higher than 20,000, yeah, with DO over D1 is less than 0.5, the CO value can be, the CO value that can be used is this, yeah, 0.16, yeah, which is valid for both gas and liquid. However, if the NRE is less than 20,000, yeah, with the other value of DO to D1, yeah, the CO value can be found in another reference or will be known in the problem. Yeah. Okay, so if the NRE is higher, oh, it's higher than 20,000. Yeah, and then the DO is 1 centimeter, D1 is 10 centimeter. So DO over D1 is 0.1. So it's less than 0.5. Also CO is 0.61. Yeah, however, if the NRE is less than 20,000, yeah, and DO and D1 is, let's say it's 0.6. Yeah. Nah, then for CO we cannot use this 0.61. Yeah, we have to find it from another reference or from the problem. Okay. Okay. So similar, yeah. It's similar to Venturi, yeah. Now, well, for the that's for the incompressible flow, yeah. While for the compressible flow, so let's say it's using the air, yeah. The flowing fluid here is air, yeah, which is compressible, yeah. So the measurement can be, we can use 3.211 for the measurement, yeah. So again, it is similar to what we have learned in venturimeter, yeah. Nah, right, same, yeah. Since velocity is, for compressible fluid, there will be a significant change in the pressure, yeah. For incompressible, there is no change in the pressure, or we can say there is a change but not much, yeah. But in the compressible, the velocity will significantly change by the change of the pressure, yeah. So that's why, yeah, we cannot use velocity, but we have to use mass or mass flux because it will not change very significant. Okay. So we use mass again. For me to change velocity to mass, I have to multiply it with A and density. That's why the density from the denominator will move up to the numerator. Yeah, and there is also A0 here. Yeah. And there's also Y it's the correction factor. Yeah, for the gas. Okay. Nah, the Y factor is similar to what we have learned in Venturi. Yeah. But since this is for orifice, so you use this, the one that is on the upper part of the Venturi method. Yeah, so for Venturi is the one in the bottom, for orifice is the one on the top here. Yeah, so for the one in orifice, we have 4 lines, dO over d1, 0.1. So the top line, and then the second line is for 0.5. The third line here is for 0.7. And the lowest part here is for 0.8, d0 to d1. Okay. Yeah, how to read it are still the same. So for the pressure ratio, we need to know first. Yeah, let's say it's 0.8, so it's here, right? And then, oh, the d0 minus d1 is 0.5. So I will drag it up until the second line here. And then again, draw a very straight horizontal line to the left until it meets the y-axis. And then you read the value. Yeah, like that. Okay. Okay, so I think that's all. Yes, for the orifice. Yeah. Do you have any questions? Yeah, if you don't have any more questions, then I will continue with the next topic. Yeah, however, if you have more questions, then you can just directly chat me, or you can just put your comment in the comment sections below. Okay. Okay, so good morning, Alpha. So I will continue the class. Yeah. So previously we talked about pitot tube and then Venturi, and then also orifice meter. Now we're going to the fourth and fifth topic, yeah, which is the flow nozzle meter and also rotameter. Yeah, and after that we will go to another measurement type for the flow rate. Yeah. So for flow nozzle meter, yeah, we will see a video first here, so that you will know, yeah, what is the difference between orifice and Venturi meter that we have discussed yesterday with the flow nozzle, because it's also similar. Yeah, so these 3 orifice nozzle and Venturi meter are 3 types of flow measurement that is similar to each other. Yeah, so the difference, yeah, you will get a better understanding by watching this video.
In numerous industrial applications, the orifice plate covers many needs of flow measurement technology. However, other designs are available for certain measuring tasks to minimize undesired effects, such as excessive pressure loss or abrasion of components due to solids carried in the fluid. This demonstration shows that an abrupt restriction generates severe turbulence in a fluid. Nozzles with a rounded, funnel-like inlet clearly reduce turbulence and thus create less pressure loss. Nozzles are particularly suitable to higher flow velocities or to fluids with abrasive solid particles. Turbulence reduction is even greater with Venturi nozzles. And finally with Venturi tubes, where the restriction is created by longer conical constrictions in the pipe wall. All these designs can be supplied with different restriction diameter sizes, so that the pressure loss and the differential pressure generated can be optimized for the process conditions.
Okay, yeah, so these 3 meter orifice, nozzle, and Venturi, the principle are quite similar. However, as orifice has the shortest head, yeah, so it cannot reduce the turbulence of the flow. Yeah, while nozzle, since it has a nozzle inside, yeah, and it's also a little bit longer than compared to orifice, because orifice is just like a double mounted plate that is welded in between the flame, so they have no nozzle. Yeah, so you know, the change from the larger pipe to the smaller one, it's very sudden, so it will, you know, increase the ADs and also turbulence. Yeah, while for nozzle, it has a nozzle attached. Yeah, even though it's not that long as compared to the Venturi nozzle or Venturi tube. Yeah, but it still has a little bit, you know, a short nozzle there. Yeah, so it will reduce the turbulence. Yeah, and by aiding the Venturi tube and as well as Venturi nozzle, yeah, the flow meter will be longer, right? And it will reduce more and more turbulence in the flow. Yeah. Okay, so we go to the flow nozzle meter. So you can find this topic in John Coplis in the page of 141. So please open the book when you listen to this class, okay? Yeah, I do not bring my 4th edition book. I only have the 3rd edition book, but this meter is not included in the 3rd edition book, so I cannot show you the theory and also the calculations in the 3rd edition book. So that's why I ask you to open your own book, because your book is in the 4th edition, right? So I'm sure there is this topic in your book. Yeah. Okay, so as you can see here, yeah, this is the nozzle, the flow nozzle meter. Yeah, so if previously in the orifice you only have two mounted plate, yeah, 2 mounted plate without any nozzle here. Yeah, that's for orifice, while for the Venturi you have a cone, right? You have a very gradual cone, yeah. While in the flow nozzle, you have a nozzle here, yeah. Okay, now, so the fluid, yeah, whose flow rate is to be measured, yeah, entered the nozzle. Okay, so the fluid coming from the big pipe here to the nozzle, yeah, smoothly, yeah, and this nozzle is called as a throat, yeah, tenggorokan, yeah, because the shape is just like a throat, yeah, where the area is minimum. Okay, so the fluid comes from this left-hand side to the right-hand side, passing through the nozzle, which we call as a throat. Yeah. Now, the length of the straight portion of the throat. Okay, so we have the throat, right? Yeah, it has a slope, yeah, on the corner, and then it goes to a straight throat. Yeah. Now, the length of the straight throat, yeah, the length of the straight portion of the throat is 1/2. So only half of the diameter of the throat. So the diameter of the throat is represented by the text D, yeah, by not capital D, yeah, while the diameter of the pipe, yeah, the diameter of the pipe is the capital D, diameter of the throat is the normal D. Yeah, it's the text D. Okay, now, so the length of the straight portion of the throat here, yeah, is only half of the diameter of the throat. Yeah, now, while for, again, yeah, venturi, orifice, and also flow nostril, meter, yeah. There are two pressure taps, yeah, that is connected into the manometer. Yeah, so similar to venturi and also orifice, this flow nozzle has also connected to the manometer. Yeah, now the upstream pressure tap or P1, yeah, the upstream pressure tap or P1, yeah, has a distance, yeah, of 1 pipe diameter from the inlet nozzle face. Yeah, so this is the nozzle face, right? Now, the distance between the nozzle face to the upstream pressure tap is equal as the diameter of the pipe. Yeah, so it's D. While the pressure tap, the downstream pressure tap 2, P2 here, yeah. The distance between the outlet nozzle face to the downstream tap or P2 is only 1/2 of the total diameter of the pipe. Yeah, so this is D, while this is D per 2. Yeah. Okay. Nah, and then to calculate the flow, the pressure drop, it is all similar to what we have learned in venturimeter and also orifice. Yeah, okay. So as I said to you, yeah, for venturi, yeah, 3.27, yeah. We can also use the same equations for flow nozzle meter, yeah. But I only changed that CV. CV is coefficient for venturi, right? CO is for orifice. Yeah. Now I will change that CV or CO to CN. Yeah. CN stands for the coefficients for the nozzle. Yeah. Okay. So the same equations, yeah, as venturi and orifice, but I have to change that CV into CN to start. Yeah, and again for compressible gases, where we will calculate the mass, yeah, mass of the fluid, yeah, M equals to Cn, yeah, or Cv or Co times Y times A. Yeah, right, you still remember, right? Now, I will have just changed, yeah, the Cv or Co to Cn only. Yeah. Okay, the expansion factor is the same for the flow nozzle and the venturi. Okay, so for orifice, yeah, for orifice is a little bit on the top, right? While for venturi is a little bit down. Yeah, now for flow nozzle, it's the same as one for the venturi. Yeah, okay, so everything are just the same with venturi, but you have to change the CV into Cn, and the expansion factor are also the same as the venturi. Nah, Okay, so the range for the Cn, yeah, for the flow nodal coefficient or Cn, yeah, it will range from 0.95, yeah, when the NRE is lower than 100,000 but higher than 10,000. Yeah, and it would be 0.98 when the NRE is in between 100,000 to 1 million. Yeah, while it would be 0.99 when the NRE is higher than 1 million. So depends on the NRE. Yeah, so if your NRE is 200,000, so it's in between this 1 million and 100,000, right? So the Cn value would be 0.98. Yeah. Nah, again, similar to Venturi meter, yeah. There is also a permanent pressure loss. Yeah, it's P1 minus P4. Yeah, for Venturi, it's P1 minus P3, right? Yeah, but here we have P1 minus P4, which can be seen in the equation of 3.213. Yeah, so where P4 is the pressure of the final and fully recovered downstream. Yeah. And beta here is D2 minus, sorry, D2 over D1. Yeah. D1 is the pipe, right? D2 is the throat. Yeah. Okay. Now, if we want to sorting the pressure loss, yeah, because the principle for orifice, flow nodal meters, and also Venturi meters are quite similar to each other. The principle, right? Nah, but the pressure loss, yeah, between those three are different, yeah, as previously mentioned in the video, yeah. So the biggest loss will be obtained if we use orifice meters, yeah, because there is no nodal, yeah, and there is no tube there, yeah. So that's why the turbulence will be very high. So that's why the pressure loss will be also higher as compared to the flow nodal and Venturi meters. And then after orifice, it will be continued by the flow nodal meters, yeah, because it is better than orifice, yeah, because it still has the throat, yeah, it still has the throat, but even though it has the throat is only very short as compared to the Venturi meters. So it is lower, yeah, in pressure loss as compared to orifice, but it's still higher as compared to the Venturi meters. Yeah, meanwhile, the Venturi meters has the least pressure loss because it has a very long tube, yeah, and a very long nodal. Okay. Yeah. If you have any questions on the flow nodal meters, then please chat me directly by using Line or WhatsApp, or you can just drop the message in the comment section in YouTube below. Yeah. Now we are going to discuss about the next flow meters, which is the rotameters. Yeah. So we will watch a video on the rotameters first. Nah, so the mechanism of the how rotameters works is that this this float, yeah, start at this, yeah. So at first the float doesn't directly float in the middle of the meters like this, but it will start from the bottom. Okay, now while the inlet of the fluid coming in, it will push the float upward. Yeah, the higher the inlet flow, the higher the inlet flow, the higher the float will be pushed upward. Yeah. Nah, and then when you want to determine like how many, yeah, or how many meters, yeah, of the inlet flow, yeah, how many cubic meter or how many liters are the flow rate for the inlet flow, then you can see from the scales on the left here or maybe scales on the right. Yeah, for the right figure, the scales is on the right. For the left figure, the scales is on the left. Yeah, and how you read this is by reading the meters. Yeah, when the float has the highest point and the largest surface area. Yeah, so if the float is a spherical in a spherical shape like this, then it's in the middle of the sphere. Yeah, so it's like around 11. Yeah, in the middle of the sphere. Okay, now if the float shape is like this, yeah. Okay, so both, yeah, both sides of this, yeah, here, this side and this side, yeah, both have a similar surface area. Yeah, however, this part, yeah, is the highest level. So actually, this is the level of the inlet flow. Yeah, so it's this, it's around like 55, 58. Yeah, okay. Yeah, okay. This is the one that I told you. Okay, so at higher flow rate, yeah, as the float rises, the annular area also increases. Yeah, so when the float coming upward, yeah, the annular area that is pushing up the float, yeah, will also increase. Yeah, so that means that there will be a lot of inlet flow, yeah, passing through the float. Okay, now, and it will reach, yeah, the float will reach a stable position, yeah, where the upward flow of the fluid, so the flow of the fluid will take up, yeah, will take over the float, right? Yeah. Now, when the upward force of the fluid is equal, yeah, to the weight of the float to come down by the gravity, yeah, if it's equal to each other, then the float will reach a stable position. Yeah. Now, and the relation, yeah, between those two, yeah, will give the flow rate number. Yeah. So, so after it reaches this height, yeah, it reaches this height, the upward flow or the upward force of the fluid equals to the weight of the float by gravity. Yeah, so it will be stable at this point. Nah, so it will give you the number of the flow rate of the inlet flow. Yeah, the flow rate value of the inlet flow. Yeah, which one? The highest point with the largest surface area. So it's in the middle of the sphere. So it's like around 11. Yeah. Okay. Now, for a given fluid density, because the fluid itself has their own weight, their own density, yeah. And then for a given fluid density of the rho f, yeah, or density of the fluid, and a fluid density of A, yeah. Now, the mass flow rate MA is given by these equations 3.214. Yeah, so please open your Giancopli's book and then see the equations 3.214. Yeah, that's how you calculate the mass flow rate of the fluid. Yeah, by using a given density of the fluid and a given density of the flow. Yeah. Okay. Now, and then if instead, yeah, I do not use the fluid density of rho A, but the fluid density of rho B. So I change the fluid from A to B. So of course the density will also change from rho A to rho B. Right now, if a fluid rho B is used instead of rho A with the same height of reading, yeah, let's say it's QA, yeah, on the rotameter, and assuming that the K does not vary very much significantly, yeah, then we can use 3 to 15. Yeah, so if I change, yeah, if I have the same density of fluid, yeah, but I change the fluid from A to B, which density also changed from rho A to rho B. Yeah, now, and it turns out that it has the same height, yeah, as when I use the rho A. Yeah, now, then I want to find the mass flow rate of B. Yeah, then we can use this 3.250. Yeah, now, and then the equation of 3 to 15 actually can be also simplified. Yeah, when we have a fluid that is coming into the rotameter, yeah, as a gas. Yeah, so let's say it's not a liquid anymore. It's not a liquid A, it's not liquid B, but it's gases. Yeah, where usually the density of the gases will be very much lower than the density of the fluid. Yeah, now then I can actually simplify the equations 3.215, yeah, to this. Yeah, QB equals to QA times square root of rho A over rho B. Yeah. Now, again, this is the one that I made a note, yeah, in the previous slides, that the reading on the rotameter is taken at the highest and widest point of the float. Yeah. So if this one have the same widest area, so I will take the highest point, which is this one. Okay. Yeah. So if you do not have any questions, then I will move to the next topic. But if you have, then please let me know. Okay. So for the last topic, which is the measurement of flow of fluids, yeah, we include this other type of flow meters. Yeah, so it is more like a theoretical topic, so I will not explain much. You can read it by yourself. Yeah, this PowerPoint, it is very, very complete already. Okay, and since it doesn't have any calculations, only a very, very few calculations, so yeah, it's better for you to read it by yourself and then understand it by yourself, and see a lot of videos that I have provided in this PowerPoint. Yeah. your senior has made it very, very complete, and I have also already add some videos for you to get a better understanding on how does this flow meters works. Yeah. Okay, so there are several. Yeah, we have turbine and paddle wheel meters. Yeah, so this is the theory, and yeah, you can see there is a GIF, yeah, that can make you more understand, yeah, about how does this turbine and paddle wheel meters work. Yeah, it's also this is the paddle one, that's turbine. This is the paddle one. The previous slide is for turbine, yeah, and this slide is for paddle. Yeah, so it's also similar. Yeah, you can read the theoretical here in the slide. Yeah, and then this, yeah, I also already put the YouTube link. Yeah, so please watch the YouTube link carefully. Yeah, so that you know how the thermal gas meters, yeah, work. Okay. Okay, and then this is also the figure. Yeah, you can try to see. Yeah, if you watch the video, I'm sure that you know how it works. Yeah, from this figure as well. Okay, the advantages, the limitations. Yeah, and then this is the heated tube design. Yeah, again, here we have the figure. Okay, and then this is for the bypass design. Okay, please see this. Yeah, the red writing here, the red writing here. Yeah, so that you know, oh, so this is explaining about this, that explaining about the other. Yeah. Okay. And this is the principle for the Coriolis mass flow meter. This is also a video. You can.
Have you ever witnessed this phenomenon? When a hose filled with water swings.
Okay, so that's also the concept for the Coriolis flow meter. And this is the vortex shading flow meter. Yeah. And again, yeah, another thing is flow in an open channel and weirs. Yeah. Okay, we have also a figure, a lot of figure here. And yeah, this is the types of the weir. We have the rectangular weir or the triangular weir. So like that. Okay, this is only a theory mostly. Yeah, only several few equations that you have to know. Yeah, but it's fairly straightforward as well. So by reading this, yeah, I'm sure you will understand. Yeah, but just read very carefully, yeah, because last year, your senior, yeah, just read this is actually the one, the one group assignment that is made by the senior, by your senior, and then they will change. I think they changed their own PPT and they read the PPTs by themselves and they do understand about the topic. So I'm sure that you can also do the same. Yeah. Okay. Later I will give you an assignment that I will post in Bella. So you can see, yeah, starting from tomorrow, yeah, what are the assignment for you? Yeah. Okay, and the deadline for the assignment, as always, it's D+1. Yeah. So it should be on Thursday at 9 a.m. in the morning. Okay, thank you very much for your attention. Then we will see you next time on Friday I'm still very sorry that I cannot teach you directly, but I will use the asynchronous or YouTube link, yeah, so that you can still have a better understanding. But I still cannot give a synchronous class because I'm still not in a very good shape right now. Yeah, thank you very much, Alpha, and see you on the next meeting. Bye-bye.